What happens in the situation where there's sufficient mass in the stellar core to overcome the electron degeneracy pressure that leads to a white dwarf?
In a champagne supernova in the sky. That haunts dismembered constellations.
Well, she said she was from a quasar, 40,000 million light years away.
What happens is an extraordinary phenomenon. The electrons and the protons are forced to fuse in a reverse version of beta decay, creating pure neutron material. Neutrons have no electric charge, so this matter can form nuclear densities. In other words, the entire star can take the density of an atomic nucleus, but of huge mass. This neutron star collapses until it's stopped by the pressure of degeneracy of neutrons themselves. That pressure leads the core to bounce, and material heads outward at relativistic speeds. This core collapse takes place in less than a second, the bounce phase in perhaps a millisecond, and the result of this enormous energy deposition outward is something we see as a supernova. Computer simulations are now good enough to simulate the extraordinary and extreme astrophysics that takes place in a collapsing massive star core. The neutron material can be simulated, the bounce phase, and the blast wave. There are other results, not easy to observe. A torrent of neutrinos is produced by the inverse beta decay reaction that leads to the neutron material. Those neutrinos were actually observed for the first time in 1987, verifying our models of this process. In fact, close to an Earth mass of neutrinos in their rest mass can be generated instantaneously in a supernova event. There's also a prediction that gravity waves will be produced, and we're waiting for LIGO to confirm that prediction. The simulations also show very clearly how much the gas is heated in the blast wave that moves out. The temperatures momentarily reach billions of Kelvin, which is easily sufficient to generate by nucleosynthesis in a blast wave all the elements of the periodic table, including the uranium elements and the transuranics, radioactive elements that will in fact subsequently decay, but all the stable elements too. The amount of energy released is so great that when the blast wave expands and cools to visible light, the dying star can reach a brightness equivalent to that of an entire galaxy, billions of times brighter than the star that led to it. We know how many massive stars there are in the galaxy, so it's fairly easy to calculate how many supernovas should occur. Because massive stars are extremely rare and their lifetimes are still long compared to a human lifetime, the event rate is low. It's predicted to be about once every 100 years. Intriguingly, there hasn't been a supernova visible in our galaxy since 1604. By Poisson statistics, or the average event rate, we're definitely due for a supernova. The last four known to have occurred in the galaxy occurred in 1006, 1054, 1572, that was known as Brahe's supernova, and 1604, known as Kepler's supernova. Tycho Brahe was lucky enough to observe two supernovae in his life, and actually used them to draw inferences that the supernovae were distant events occurring beyond the realm of the planets. What happens when a nearby dying star brightens to the brightness of an entire galaxy? Well, in these four instances, the event becomes visible in the daytime sky. So if a supernova went off relatively near us, it would be a phenomenal event. It would actually be so bright that astronomers would have trouble studying it, because it would saturate or burn out the detectors on their large telescopes. Amateur astronomers would have a field day, and anyone with a telescope smaller than a meter. Evidence in particular of the 1054 event is found around the world in petroglyphs, rock art, and records of old civilizations. The Chinese called it a guest star, and it was clearly visible in the sky for weeks. This is the brightest of the known supernovae that have occurred in human history, but statistically there must have been many more in the times before people kept written records. We can only guess what ancient civilizations or cultures or hunter-gatherers must have thought when a star suddenly brightened enough to rival the sun. Astronomers of the modern era haven't been lucky enough to find a supernova in our galaxy. On the other hand, be careful what you wish for. If a supernova went off within 10 or 15 light years of the Earth, it would be bad news for life on Earth. But at a safe distance of perhaps 100 light years or 200 light years, it would be a spectacular event. In the history of modern astronomical detectors, only one supernova has been extremely easy to view, and that was the supernova that occurred in 1987 in the Large Magellanic Cloud, the nearest galaxy neighbor to the Milky Way. The Magellanic Cloud is 170,000 light years away, So that's the time it took the signal to reach us. So you can imagine the situation. A star died in our nearest neighbor galaxy before humans left the plains of Africa to fan off around the world in their migration. That light wave passed through space, deep space, reaching the edge of our galaxy as human civilization started to form. And then, 20 or so years ago, the light wave swept past the Earth. This was an event where the neutrinos slightly preceded the light, and a handful of neutrino events were seen in a Japanese detector called Kamiokande. It was a wonderful kickstart to the idea of neutrino astronomy, which is now rapidly maturing. The 1987A supernova allowed us to test our models of how stars die, confirming some of the ideas and disproving others. It's so far the best testbed for theories of supernovae. On the dark material there. Supernovas form in two different ways, called type 1 or type 2, although subclasses have now been defined. In a type 2 supernova, an isolated massive star dies explosively. In a type 1 supernova, the system is a binary system where the star is triggered to supernova event by the passage of material in a binary orbit. Material can siphon from one star to another when they're fairly close, within say 100 or 1,000 times the radius of either of the stars. This is a particularly tight orbit. Most binary stars are in much wider orbits. The supernovae that occur in a binary star system are particularly valuable to astronomers because of the regulated way the mass is transferred. The explosion has a very well regulated and typical amount of energy, constant between systems to within 15%. This means it acts as a standard bomb or a standard light bulb in the sky, allowing astronomers to use it to calculate distances and do cosmology. With no current or very recent dying stars to observe, we're left looking at supernova remnants, the enormous illuminated shrouds of gas and glowing dust that are seen distances of tens or hundreds of light years away and times of centuries or millennia after the supernova went off. The sky is littered with evidence of dying stars in previous times. The Veil Nebula is a beautiful form that's been imaged with the Hubble Space Telescope, and Tycho's supernovae has been imaged with the Chandra X-ray Observatory. It's recent enough that it's still glowing in X-rays. In this animation, we observe a supernova explosion as a pure animation, but it ends with the actual Hubble Space Telescope and Chandra data showing the illumination of the gas and the incredibly complex patterns that are formed in the interstellar medium. We're now not only in a position to explain the cosmic abundance of the elements in the periodic table, but element by element to say where those elements were produced and how. It's easy to see. There are the primordial elements, hydrogen and helium, and then a set of heavier elements produced in massive stars. But the vast majority of the heavy elements throughout the periodic table are produced in the more evanescent late stages of a massive star's life, either by the slow ingestion of neutrons gradually bumping up the atomic number by one, or by the violent and explosive addition of nuclear material in a supernova blast wave. At the end of a star's life, if the massive core is too big to be supported by degeneracy pressure of electrons, the star collapses, bounces, and detonates in an enormous blast wave, going off into space and carrying much of the star's total material, called a supernova. The average rate of supernovae in our galaxy should be about one a century, and since the last one occurred over 4 centuries ago, we're due. If a supernova occurred nearby, it would be a spectacular event, rivaling the sun in the daytime sky. Supernovae are responsible for creating many, if not most, of the heavy elements in the universe, including gold, silver, platinum, the precious elements, and even the transuranics.